Good morning, good afternoon, and good evening, everyone. Welcome to the Combustion webinar. Today, I would like to introduce you our speaker. It's Professor Jeffrey Bergthorson. He's a Panda faculty scholar in sustainable engineering and design, and also a professor in the Department of Mechanical Engineering at McGill University, where he leads and also founded the Alternative Fuels Laboratory. He received his bachelor degree in mechanical engineering from the University of Manitoba, and also his master and PhD degrees in aeronautics from the Graduate Aeronautical Laboratories of Caltech. Professor Bergthorson is a fellow of the Combustion Institute and also a fellow of the American Society of Mechanical Engineers. Professor Bergthorson's research interests are in the broad area of the combustion and emissions properties of alternative and sustainable fuels, which includes biofuels, hydrogen, and the use of metals as carbon-free recyclable fuels, which is the topic of his talk today. And then I will now give the virtual podium to Professor Bergthorson, and let's look forward to his interesting presentation. Please, Jeff.
Thank you very much, Xiaocheng. Well, great. So, I want to start today just talking a little bit about what we hope to discuss. The messages that I hope you take away today from the webinar are that we can use these metals as a way of storing clean energy in processes that are free of any carbon dioxide or other greenhouse gas emissions, and that enables us to have a method of transporting and storing renewable energy and decarbonizing the economy and really decarbonizing the hardest sectors of the economy to go to zero carbon emissions. There are two real ways that we can use these metals to harness their power. And the first is to react them with water and generate hydrogen and heat on demand. And that idea comes from the area of rocket propulsion, where aluminum and other metals have been considered as green propellants. And the other way that we can use them is to burn them with air and produce heat. You see the flame on the right-hand side here. I'll just reboot this. That's a flame of iron particles burning in air. And the particles can burn, release heat, and we can then harness that heat as it's the product itself, or we can use that heat and convert that into motive power or electricity using similar systems that we have today, such as steam cycles or Stirling engines. What I want to talk about in terms of the combustion science is what is unique about metal combustion is really the fact that these little particles, as you can see here in the case of the sparkler, can be ejected and burned by themselves in cold air around them. And so that means that they can burn as little micro-reactors. And because they burn like micro-reactors, they're able to burn independently of the gas that's around them. And that ability to burn and release heat at discrete points in the flow means that they have different combustion physics from the traditional fuels that we're used to dealing with. And that leads to a new type of combustion physics called the discrete regime of particle combustion, or discrete flames. And that means that we've got to develop new science for how to understand the propagation, stabilization, and the limits of those four metal flames. And I want to close with a whole bunch of questions, and there's many more that I won't talk about today, but really that this is an area that's still very much in its infancy, and we've got lots of things still to learn, and that's an invitation to the young people to look at this. So when I started the Alternative Fuels Laboratory 16 years ago now, the goal was really to try to find solutions to these key problems, right? Fossil fuels are awesome. They have extremely high energy by unit mass, called the specific energy, and extremely high energy per unit volume, the energy density. And that means that we've used those to develop all of our modern economy and the prosperity that comes along with it. But we know that there's problems associated with using fossil fuels. There's limited resources, costs are going up, and of course the emissions of carbon dioxide are leading to climate change. So we need to find solutions and alternatives to decarbonize the economy for those reasons, to maintain prosperity in the long term and to make sure that we are not harming our environment. And so when I started working on these problems, the idea was, well, let's just use the natural processes of plants grow, they draw the carbon dioxide from the atmosphere, we can make a biofuel out of those, we can burn that, and of course the CO2 is released, but that cycle gets closed by nature. And that's interesting. There's a lot of work going on in the biofuels area, but the real challenge associated with that is that the amount of growth of biomass is simply not enough for us to run our whole economy on that. So the amount that we can draw sustainably in terms of biomass is not going to displace all of our energy needs. And so then people say, well, what about we just take clean energy and we won't use nature, but we'll actually draw carbon dioxide out of the atmosphere using direct air capture and use that carbon dioxide. We can react it with hydrogen and we can make synthetic fuels that way. That's called e-fuels. And that concept, for me, doesn't make a lot of sense, because if we've gone to all that work to draw that carbon dioxide out of the atmosphere and our goal is to reduce emissions, we should use that carbon for something else and not put it into a fuel and burn it right away. So we want to find some other solutions besides carbon-based fuels, in my opinion. And what we really are looking for is some type of recyclable energy carriers, because sustainability to me really means closing the loop. You need to take that same material and use it over and over again. And by the use of that material over and over again, instead of taking something from the ground, using it once and throwing it away either to the atmosphere or to the landfill, if we can close that loop and use that material over and over again, then we can have prosperity into the long term. And that's the idea behind really all aspects of sustainability. It's really about that circularity of materials. And so the goal is, of course, to have no carbon emissions either at the point of production of those energy carriers or at the point of their consumption. And when we look at this sort of energy storage concepts, really the only ones that scale to the sorts of large scale, full economy scale are going to be chemical energy carriers. Other types of energy storage make sense locally, small scale for relatively light duty and relatively low range type of applications. You can get away with batteries. And then for energy storage locally, you can do pumped hydro, compressed air, these sorts of things. But when we want to decarbonize the full economy, we're going to need chemical energy carriers. That's very clear. And so the challenge, of course, about making fuels from electricity is that traditionally we've taken fossil fuels from the ground that are relatively cheap. We've burned them in power plants and we've produced electricity. And that means, by definition, electricity has traditionally been more expensive than the fuels with which you've used to produce that. But with the decreasing costs of utility scale solar energy, wind, and other renewables, we're now getting into a situation where we can have electricity prices that are actually cheaper than the fuel prices. And as that gap increases, renewable electricity goes down in cost and maybe fossil fuels go up in cost. That opens up an opportunity to actually make these energy carriers cost competitive. And so then the question is, what are the options available to us and which ones should we be pursuing? So most of the attention out there in the field these days is on the use of batteries for light duty transportation and hydrogen for other things. And hydrogen is a great fuel, as we know. I mean, it's an extremely large amount of energy per unit mass. It's just got that one proton and the electron in the hydrogen atom, and that means it's got a lot of chemical energy per unit mass. So that's a high specific energy. But the problem with hydrogen is that it has a very low density, even as a cryogenic liquid. And when you take into account the weight of the storage tank, then the actual energy density of the hydrogen storage system is not nearly as good. And this is the US Department of Energy ultimate hydrogen storage target, which to my knowledge, no technology currently can meet. And you can see that it's quite a bit below where we are at with fossil fuels. Lithium-ion batteries, because they carry all of the reactants on board, thermodynamically, you just simply cannot have a battery that's going to approach the energy densities of a fuel that you can burn with the air, because you get the air, the oxygen from the air for free. You don't have to carry that around with you. And so that's those are some key challenges associated with the sort of current options. And so within my team, we wanted to look and find other solutions. And so if we want to look and say, what are the possibilities out there? We can look at the periodic table of the elements and understand that that's what nature's given us. This is our options. So we have to look and say, well, what of these things can be possible energy carriers that can avoid or answer these needs that we've discussed? And we can eliminate large swaths of this periodic table very rapidly. We know that things on the right-hand side of the periodic table are oxidizers. They're not fuels. They're not going to be useful to us in this goals. If anything is in the lower ranks of the periodic table, it's heavy, large, they'll have low specific energy. They're not going to make sense. We can eliminate some other ones. If they're very rare, that means they're going to be expensive. If they're toxic or their oxides are toxic, then they're not going to be fitting into this idea of a green fuel. If they react too slowly with air or with water, then they're not going to be a very valuable fuel. And similarly, if they're too reactive, like sodium, potassium, and whatnot, then those fuels are too dangerous to transport and store. And so we can eliminate those. We see that when we look at this table, we've got hydrogen up here, we've got carbon up here, the backbone of all of life and all of our current fuels of interest. We can eliminate those because we've talked about the reasons to move to other options. And if we look at the rest of the options here, they are all metals or metalloids, lithium, boron, magnesium, aluminum, silicon, iron, and zinc. And those are all metal fuels or metalloid fuels. And so to understand which of these metals might make sense to use as a recyclable fuel, we can then take these and look at what is the availability of these resources. So we did a crazy calculation. We first took these metals and said, how much of the metal would be required to power the entire Earth for 1 year? Currently, we use about 500 exajoules of energy. And so the amount of mass of metal to provide 500 exajoules would scale directly with or inversely with their specific energy. So you need less lithium because it's a lighter element, and you need more iron or zinc because they're heavier elements. But that doesn't tell us very much on its own. I mean, sure, it's a lot. It's hundreds of gigatons. That scales with the fact that we're using a lot of energy as a society today. But we can compare these amounts of fuel that would be needed to the reserves or the resources of those. And when we look at that, we see that some of these metals make more sense maybe than others, and at least scale to that very large scale and can provide perhaps the most cost-effective energy storage solutions. And we see that things like iron, aluminum, and silicon really have vast reserves, and iron and steel are by far our most produced metals on Earth today. Other things like lithium, well, there's been a lot of discussion about the issues associated with lithium reserves for the full decarbonization of the economy. And so we probably want to try to find other solutions. And by bringing more of these into the mix, then that gives us even more options and should lead to even lower costs. And so the concept of metal fuels is really this. You take clean energy, you reduce the fuel from its metal oxide in some type of a clean process to remove the oxygen from it. You then transport that fuel, and then you oxidize it, burn it, or react it with water where you need that energy. And that enables you to separate out primary renewable electricity from where and when we need it. So you make the energy in locations where you have abundant renewables, and you use it where and when you don't have those renewables available. And so when we look at these, we'll say, okay, well, but doesn't the metallurgical industry have a high amount of carbon dioxide emissions? And the answer is yes, it's some of our biggest emitting sectors today. Right now, aluminum, for instance, is made through the Hall-Héroult process using carbon anodes derived typically from coal that are hardened carbon anodes. And as that aluminum is reduced primarily with electricity, the carbon anode is consumed. It grabs the oxygen off of the alumina or the bauxite, and then is releasing stoichiometric amounts of CO2. But researchers are developing, and now industry is developing inert anodes. And in an inert anode, it's very similar to a water electrolysis process where you just pull the oxygen off of the metal, in this case, aluminum, and produce aluminum without any carbon dioxide emissions in the cell. And that's being commercialized by a company called Elysis that is a spinoff from Rio Tinto, and Apple has bought the first green aluminum. And so that's now actually been commercially produced today. And so you can buy carbon-free aluminum. If we look at iron, iron has typically been produced through blast furnaces, basically since the start of the Iron Age. And that's been using carbon as a reductant, and carbon and coal is a great reductant for iron because it grabs that oxygen off of the iron at high temperatures. But it's possible to reduce iron without carbon emissions. And that has been done and demonstrated at scale using the Midrex process driven by hydrogen. So there you would produce hydrogen via green electrolysis or some other process, say capturing the carbon emissions from a natural gas reformation process, and then using that hydrogen to reduce the iron. and from iron oxide into iron. And if you do that, then you can basically store the energy from the hydrogen in iron rather than as compressed hydrogen or liquefied hydrogen, and use that as a way to store the energy from the hydrogen. It's also possible to do a direct electrolysis of iron oxides into iron. That's been developed by ArcelorMittal, or is being developed in the Siderwind process, which is a low temperature electrolysis process to produce iron from iron oxide. And then there's also a company, Boston Metals, that does high temperature molten oxide electrolysis to where, again, there's no carbon emissions associated with it. So we can produce metals without carbon dioxide emissions. It's not a requirement to have greenhouse gases, even if we have large amounts of that today. So we can produce the fuel cleanly, but what about using it? How are we going to make use of it? Well, when we look at these different metals, we can plot them on this specific energy and energy density diagram. We can see that the light metals like lithium and aluminum have very high specific energies, very close to our traditional fossil fuels. Things like iron are heavier, and so therefore they have lower specific energies. And then we can look at the energy by volume, and these metals are very dense solids, and so therefore they have a lot of energy per unit volume. And this is the reason why aluminum, for instance, has long been used as a fuel inside of rocket propellants, is because of this high energy density and specific energy, amongst some other benefits. And so we can burn these metals. Here's images of the McGill Bunsen burner, where we have a methane flame stabilized on it, recognizable to all of us. And here's an iron flame burning about 1 to 3 micron iron particles. It's burning orange hot, so that glow of orange is coming from the iron oxide products, and the temperature of that flame is around 2000 Celsius. In the case of aluminum, this is about 8 micron aluminum particles burning in air. The temperature of that flame is over 3000 Celsius, so it's burning white hot. In this flame is so bright in the laboratory that you have to look at it with welding goggles. This picture's been taken through a bunch of neutral density filters, but it's extremely bright and very energetic. We can also react very reactive metals with water. And as I said, that's been used as a green propellant by researchers at Penn State and Purdue University. Steve Sun is here in the panel. And so this is an image of nanometric aluminum particles mixed with water, burning in a strand. And you can see the flame propagating down, producing hydrogen at about 3000 Kelvin as the product. And that was used to launch the Alice aluminum ice rocket in a demonstration product. And in either case, whether you burn them in air or you react them with water, the product is a solid metal oxide, and that can be captured, stored, transported, and recycled to close that loop, as we talked about. There's no emissions of carbon dioxide, carbon monoxide, unburned hydrocarbons, soot, any of the other emissions. The only emission really of concern when we're talking about metal fuels would be nitrogen oxides or metal products that escape our capture system that we have to be concerned about. So taking these two ideas of burning metals or reacting them with water, we proposed 2 different cycles. We call them the dry and the wet cycle. So in the dry cycle, you take metal fuels, as a powder, you suspend them in air, you burn them to release their heat, and you take that heat and you generate electricity via a steam engine and a Stirling engine, or you can use that heat directly. In the metal water system, or the wet cycle, you take the metals, you react them with water, you produce heat and hydrogen or hydrogen steam mixtures, and then that can be fed to gas turbine engines, reciprocating engines, or even fuel cells. So we can use these 2 different types of technologies for different applications where and when it makes sense. For example, the wet cycle might make sense where you're on the coastal regions where you have abundant water available, or where or for shipping, let's say, whereas the dry cycle may make more sense where water is more scarce. And so we'll talk just very briefly about the wet cycle. I mean, why we're interested in this concept is that if we take a liter of aluminum and we react it with water, stoichiometric amount of water, we get the heat equivalent to burning a liter of diesel. So already that's our fuel that we're trying to replace. Plus we get the equivalent of 4 liters of cryogenic hydrogen. So that just speaks to the energy density of this aluminum. It's great stuff. It's basically solid electricity, if we think of it that way. And so we've developed over the years a research program looking at this metal-water reaction, and showed that if you go up in pressure and temperature up past the critical point into supercritical water, we can take bulk aluminum. These are aluminum slugs, 2 millimeters by 3 millimeters, And if you cross that critical point, you can basically digest them into aluminum oxide powder and achieve yields that are basically stoichiometric yields of hydrogen. So you get the reaction completeness. There's no more leftover aluminum in the reaction products. And it works with scrap aluminum and basically, and multiple aluminum alloys as well, and with other metals that can also be reacted with water in this way. So that gives us a way of transporting and storing energy and producing hydrogen on demand, which fits in then to some of the other technologies that we're developing as part of the hydrogen economy. But this is a combustion audience, and there's not really combustion there unless you go to the propellant mode, and there's other people who can speak to that, to the combustion of metals with water better than I can. So what we really want to talk about today is what is the combustion physics behind burning these metals with air to produce heat. And so we can look at this and say, what's special about these metal flames? And as I said, really the unique feature of metal combustion is that you cannot premix metal vapors with oxygen in air. So whereas when we burn coal or even liquid droplets of hydrocarbon fuel, often the fuel vaporizes at least partially and mixes with air, and we have some type of premixed combustion process, or at least a homogeneous combustion process between gases. In the case of metals, they react so rapidly with oxygen that they won't premix with air. And that means that the reaction is almost by definition in a non-premixed and heterogeneous mode. And so that fact means that we have these heat released close to the particle surface. And that's what enables these little particles to ignite. Here's a titanium particle injected into hydrocarbon fuel. You can see it comes at some point, it ignites, and then it burns over some type of combustion time. In the case of titanium, it explodes in a little spark. Or like our sparkler, right? In the sparkler, we have a hydrocarbon binder that's burning, propagating down, ejecting these metal particles, and then they burn as little microreactors inside of the air. And in the case of iron with carbon content, could explode in little sparks at the end. So let's understand what that ignition process is all about. So when we have a heterogeneous combustion process, there's two processes taking place in order to enable that combustion. There's a reaction at the particle surface, which will follow some heterogeneous kinetics. And then there's a rate of diffusion of the oxidizer to the particle surface. And so the surface reaction, depending on the metal and the fuel, will have different forms. Here in this early work that we did that follows along from the classical work by Frank Kamenetsky and Vullis, we just looked at a simple one-step heterogeneous reaction given by our traditional Arrhenius reaction rate form. The oxygen diffusion, that can be modeled assuming just a stationary particle in a flow by the simple diffusion equation that we have here. And you can combine those two to derive an effective kinetic reaction rate or effective reaction rate that depends on the interplay between the kinetics and the diffusion processes. And so the rate of heat release will be directly proportional to the rate of this chemical reaction. And then the heat loss rate will be proportional to whatever convective heat transfer coefficient that you have and the temperature difference between the particle and the surrounding gas. And so if you take a particle of metal and you put it into a cold air, then the reaction rate is going to be relatively slow. The heat transfer rate and the rate of delivery of oxygen to the surface is going to be fast, and the temperature of the particle will be very close to the temperature of the gas. And in fact, we can look at the reaction rate form here of this effective reaction rate and say, well, what does that look like as a function of temperature? Well, initially, it increases exponentially because of the kinetic reaction rate, the exponential dependence on temperature. But then at some point, the diffusion limit will take over, and then it will burn at a rate that's much weaker sensitivity to temperature. And so it will fall off as we go to the high regions. So initially it's burning in the kinetic limit, but the reaction rate is so slow that basically the temperature of the particle and the gas are almost equal to each other. And that's what we call the kinetic regime of particle burning, where the particle temperature is just slightly above the temperature of the gas, and basically they're in equilibrium with each other. But then let's say we heat up the particle, either by putting it in burning some hydrocarbon fuel, we hit it with a laser, we hit it with a spark, some other method to raise the temperature of the particle and increase the reaction rate. Well, as the reaction rate of the particle increases, it will go through a critical point, just like our standard Semenov explosion theory that we learn in Combustion 101. And it will then transition from a stable state in the low temperature regime to a stable state inside of the diffusion limited combustion regime, where now the temperature of the particle approaches and or equals the temperature of the stoichiometric mixture between that metal and the oxidizing gas that it's in. And that's what's called the diffusion regime of combustion, when it's burning as a little microreactor at a temperature that's much higher than the surrounding gas. And so to understand this process of particle ignition, we can think about it in terms of the temperature of the particle versus the temperature of the surrounding gas. And we'll normalize both of those by that adiabatic temperature of the stoichiometric mixture. And we can look at the stable states where the rate of reaction equals the rate of heat loss from the particle. And so the diffusion limit is when the temperature of the particle is equal to the stoichiometric adiabatic flame temperature. The kinetic limit is when the temperature of the particle is equal to the gas. So that's a line on this plot. And so initially, if we look at very large particles, well, for low gas temperatures and particle temperatures, the particle will be burning in the kinetic regime. And then as we increase its temperature, we'll find a critical point, and it will then transition to the strong or high temperature branch, just like we learn about in well-stirred reactors, flame theory and flame quenching, and burn now in the diffusion regime of combustion. And for very large particles, actually, once it's ignited, it may not be possible for that particle to ignite. In this case, we can see that there is no left side of the S curve. But if we go to a slightly smaller particle, then we can see that we get that classical S curve that we're used to from well-stirred reactors and other things in our combustion courses. And so as we raise the temperature of the particle, it ignites, it can burn in that diffusion regime. And then if the surrounding gas gets colder, the particle burns out, the rate of reaction slows down, it can eventually extinguish or quench back and burn into the kinetic regime of combustion. And maybe in this case, if that happens, then it would leave some unreacted metal in the core of the particle. As we go to even smaller particles, those points of ignition and extinction move closer together. And for very small particles, it may actually be possible that there is no ignition point anymore, and that they come together, and we now get a situation where the rate of heat release or the temperature of the particle is a continuous function of the surrounding gas temperature, and there may not be any ignition process that's possible as we go. So that's the unfolding of the S curve that also we can see inside of our combustion textbooks. So, okay, so that's what particle ignition is, and that's what enables these little burning iron particles that are leaving this flame to keep burning in the surrounding cold air as little micro-diffusion reactors. And they're also burning, you know, as these little diffusion reactors or little flames within the flame inside of that larger flame structure. And so the question is, well, okay, so what does that mean? How does that change the combustion physics? So we can look at, what does this mean? If we have large particles that can ignite inside of a flame, well, then that means that inside of the reaction zone, they will ignite when they reach some temperature and burn in the diffusion regime at a temperature that's higher than the surrounding gas. And so there will be a temperature difference, at least for lean flames, between the temperature of the particles and the temperature or the adiabatic temperature of the flame. And that temperature separation is an indication of the transition to the diffusion regime of particle combustion. And so you can look at a model. Here's just a very simple one-dimensional flame model following the Spalding approach. This is a video of an iron flame burning in microgravity from some experiments that Sam Garoshin and Andrew Higgins had done previously. And you can see here what that flame structure looks like dynamically. We have the radius of the particle. So in this case, the particle is being consumed. And because this is a stoichiometry of a half, the oxygen concentration drops to half of its initial value. And we can define a Damkohler number, which tells us the interplay between those two different rates. And you know, that Damkohler number approaching 1 means that the particle is burning in the diffusion regime of particle combustion. And we can see that the heat release, the Q here, is localized into a relatively thin zone, although thicker than a traditional hydrocarbon flame. If we go to very small particles now, those that can't ignite necessarily, we can still have a flame. So particle ignition is not necessary to burn these metal particles, they can burn in the kinetic regime at the temperature that's the adiabatic temperature of the mixture. And so for small particles, even if they don't ignite, we can still get a flame, and that flame can propagate. And we've seen that in some experiments that I'm not going to talk about today, and demonstrated that this is possible. So you can burn those particles in the kinetic regime. And in that case, really the flame looks very much like a standard hydrocarbon flame in the kinetic regime. No temperature separation inside of the reaction zone, and a very thin reaction zone. And the Dam Kohler number stays close to 0, which means that it's burning in the kinetic regime. Okay, so that's theory. Now let's go to some experiments. So Sam Grosjean developed at McGill in the 90s, the McGill Bunsen dust burner. Basically, the way it operates is that you have a packed bed of metal particles, a piston that moves at a controlled rate to move those particles into a circumferential jet, a very high speed concentric jet that comes in, lifts those particles and makes a turbulent flow to loft them. Then a long tube to stabilize and laminarize that flow. And then that's how we can stabilize those Bunsen dust flames. In these experiments, we wanted to study this in a flat flame geometry, going to the type of counterflow flames that we're used to studying inside of combustion and that I worked on for hydrocarbons back in my PhD. And so we made a hot product counterflow. So basically a methane air flame inside of a ceramic nozzle that could blow hot combustion products and stabilize this now as a counterflow or flat flame, enabling us to then do laser diagnostics on it. And so when we look at this, we can first look at the temperatures. And there's good evidence to our eyes that the particles are igniting and burning, but we don't know. Maybe these are just agglomerates that are being ejected, and maybe inside we don't have ignition of the particles that are the finer ones. So let's look and see what we can learn from measuring the temperature inside of these flames. So these are flames of 1 to 3 microns iron powder, burning in oxygen-argon mixtures. As we go up in oxygen concentration, the predicted flame temperature actually decreases because you're replacing the low heat capacity argon with higher heat capacity oxygen. And because these are fuel-lean flames, you're still going to release the same amount of heat from burning the iron. So the predicted adiabatic flame temperatures of the mixtures are going down. We can measure the temperatures in these different mixtures. Here it is for 30 and for 40%. And we can see via pyrometry that we have an increase in the intensity and an increase in the slope of the emissions from the black body radiation from those particles. And that we can use and fit to Planck's law or Wien's law and see that the temperature of the 40% oxygen flame is significantly higher than that in 30% oxygen. And we can see individual point measurements from those and the average of those measurements. We can also plot on here the stoichiometric concentration, and that increases because if you have more oxygen inside of the mixture, then you can burn more iron and you can release more heat and have less inert gas along with it. So therefore you get an increase in that temperature. And so the fact that we see that temperature separation between what is expected for the average flame temperature and what we measure for the particle burning temperature, that's strong evidence that the particles are in fact igniting and burning in the diffusion regime of particle combustion, even though they're relatively small, 1 to 3 microns of iron powder. And that we've explained and understood with some work that Xiaocheng has been doing, and that I'm not going to talk about today, but we understand now that iron kinetics don't depend on the surrounding gas oxidizer concentration, and that enables them to ignite for really small particle sizes. And so those particles ignite and burn, and that leads to these little micro-diffusion reactors inside of there and those flames within the flame. So what we want to understand then is, okay, so we know that they're igniting, but let's look now at the flame propagation characteristics and understand how we might actually stabilize such a flame. So we can use particle image velocimetry just like we would do for hydrocarbon combustion. In this case, we don't need to seed with any seeding particles because the iron particles themselves can be used to track the velocity of the flow. So here's some high-speed camera imaging with a laser passing through. This is actually from an aluminum flame because I have this nice video and you can see the aluminum flame reaction zone is here and the particles moving into that flame. And so when we measure the flame speed for these fuel-lean mixtures of iron flames in different concentrations of oxidizer, we have here the results for 21% oxygen and argon, 30% and 40%. And so we know the temperature of the 40% burning particles is significantly higher. From other experiments, we know that the rate of that combustion in the diffusion limit, and from the theory, should be at least twice as fast. Those particles burning at 40% oxygen should be releasing their heat twice as fast as in 21% oxygen. So the reaction rate is doubled, and yet the flame speed doesn't increase. And if anything, it looks here like it decreases, although there's significant experimental uncertainty here. So we'll call it that the flame speed is sort of constant. And that's very strange. So why? And that's the question that we want to understand. Well, the theory behind why the flame speed doesn't depend on the rate of reaction of those particles was developed by Sam Goroshin, who's been working with us at McGill for some time, back even before he joined McGill. And he showed through some theory developed with Yuri Shoshin that this effect can be explained by one simple parameter inside of the flow, a dimensionless parameter called the discreteness parameter. And the discreteness parameter is basically the ratio of the combustion time of the single particle compared to the time it takes for the heat to transfer from particle to particle. So the combustion time of the particle, that's just the particle burn time that we can measure and or estimate via our theory. And then the heat diffusion time just depends on the thermal diffusivity of the gas and the average distance between the particles. And so in the continuous regime, when we have the combustion time being very long and the heat transfer time being relatively fast, the temperature field smooths out and that flame will propagate relatively uniformly. You can see the fact that the heat's released in discrete points in the flow doesn't really change the flame structure. And these simulations were performed by Fred Lam and Andrew Higgins and Xiaocheng some years ago. And so we see then we get the continuous front of the flame. But when we go to the other extreme, when the particles burn really fast compared to the time it takes for the heat transfer between particles, well, then the flame doesn't look like a flame anymore. So this is a zoomed in view, and you can see that the particles are igniting one by one, releasing their heat, and that heat spreads out via diffusion through the mixture. And instead of being a flame like we would think about, it's really a series of explosions where the energy is released in a pop, 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 as the heat transfer field ignites those next particles inside of the system. And that's when we get into the discrete regime of combustion, when now the reaction rate or the speed of the flame is controlled rather not by the reaction rate of the particles, which is relatively fast, but by the rate of heat transfer. And so for that continuous regime, that follows our standard theories for combustion, really what we've learned about in our basic combustion class, that the flame speed depends on the square root of the thermal diffusivity and the reaction rate. And the reaction rate is just 1 over the combustion time, so it's just alpha over the combustion time here. But in the case of the discrete regime of particle combustion, now the scaling is completely different. The combustion time is so fast that it doesn't matter anymore. And so the flame speed scales by the thermal diffusivity divided by that distance between the particles. And that's a new type of flame. So in order to understand and assess this theory and to try to validate this theory, Andrew and Sam had worked on developing an experiment funded by the European Space Agency called PERWaves for percolating reactive waves and particulate suspensions. Based on many years of work on microgravity experiments on parabolic flight aircraft, both with NASA and then with the Canadian Space Agency. And the idea was to try to force the mixtures to go into the discrete regime and use microgravity to stabilize a suspension of these metal particles that wouldn't settle and would enable us to then to study the combustion physics. So an oxygen xenon gas mixture was used to try to reduce the diffusivity, and iron particles are used because they burn mostly in a heterogeneous combustion mode. You can see the individual particles burning, and they have a well-defined ignition temperature and combustion time that can be assessed on the ground before the experiments. So Jan Palechka, PhD student working with me, studied the combustion of the individual particles in 2 different gas mixtures. We doubled the oxidizer concentration between 20 and 40% diluted in xenon. And we used large particles to try to accentuate and make the L bigger. And so we had a little apparatus in the lab, a little drop tube furnace held around 800 Kelvin with a higher temperature in the top section. injected those metal particles, iron particles, into that mixture in 20% and in 40% oxygen. And the two different mixtures, we can see that there's a significant difference in the combustion times of those particles. So this is taken with a high-speed movie, and you can see in 20% we get this long combustion tail. And I can't actually, with this zoom window, I need to move it. There we go. And in 40%, we see the combustion process is much more rapid in 40% oxygen. In fact, when we made measurements of the average combustion time of these particles, it was about 8 milliseconds in the 20% mixtures and 2.7 milliseconds in the 40% oxygen mixtures, which is about 3 times faster than in the 20%. So diffusion limited combustion theory would tell us that it should burn twice as fast. The combustion time should be half of that. But it's even faster because we can see evidence here that the flame is enlarged for the 40% oxygen mixture. And there's evidence that actually you have some evaporation of iron and the combustion happening inside of an enveloping flame between some evaporated iron and or iron oxide and the surrounding oxygen. So that enhances and speeds up the reaction even further than just simply the doubling of the rate of diffusion of oxidizer to the surface. And both of these suspensions are predicted to have discreteness parameters well below 1 and should be in the discrete regime of particle combustion. So the team from McGill, Andrew is here, and Jan and Sam are here, along with the team from Airbus that developed the hardware and the other experiments here, launched from the northern part of Sweden in Kiruna, this experiment on a sounding rocket. And so the Maxis 9 rocket launched, and the question was, well, can we see evidence for this discrete regime of particle combustion? So the way the experiment worked is very simple. You have a transparent glass tube, you disperse the metal powder inside of it. We wanted to know the concentration, so we illuminate with a laser sheet and try to measure the particle concentration with a particle counting camera. We then ignite the mixture, and the flame propagates upwards through the tube, upwards or downwards, doesn't really matter in microgravity, and then image with a flame speed camera looking at the whole tube, and another camera zoomed in to image just the structure of the flame at a higher resolution. Because each time that you run one of these flames, you get a large chance of having iron oxide particles or unburned iron particles coating the inner surface of those quartz tubes. That meant that you couldn't use the same tube over and over again. So a carousel with multiple tubes was used that enabled those to clock. Each time a new experiment was run, a fresh tube was brought into the experiment. And because we wanted to study the difference between 20 and 40% oxygen, there's 2 different gas mixtures and 2 different carousels to do that. And that's what the hardware looked like in the experiment. So, okay, so what happened? Well, here you can see at the ignition event, to ignite these flames, a little bit of propane was injected at the closed end of the tube, open end of the tube, pardon me, and that ignited with a spark in order to get the flame to propagate. And that ignition event was relatively violent, but then by about 1/3 of the tube, we get the flames propagating in a more stable state. You can see the large difference in brightness. And in fact, the contrast has been adjusted here between the 20% and 40%. That's strong evidence of that difference in temperature and the difference in the burning rates. But when we look at those 2 videos, we see that even though these particles are burning 3 times faster, that the speed of propagation once it settles down appears to be relatively consistent between those 2 mixtures. So let's actually look at what the data says instead of just the videos. And so from multiple shots that we got stable flame propagation inside of the tube, we can compare the flame speeds as a function of the oxygen concentration, the metal particle concentration. And the speeds are very slow, about 1 centimeter per second, something that you could never study on the ground. But we see that even though we have that difference in combustion time between those 2, that the flame speed was consistently there around 1 centimeter per second for both mixtures. If we look at what the theory would predict, the theory for the continuous regime would predict that about a 3 times faster combustion process in the 40% oxygen and a slightly higher diffusivity in the 40% oxygen case, because oxygen has a higher rate of diffusion than xenon. So that would lead to about a prediction of about 2 times faster flame speeds in the 40% mixtures. Whereas the discrete combustion theory predicts that there would be about a 20% variation, just really due to that difference in the thermal diffusivity that comes along with that enhanced diffusion rate from oxygen. And so we look at that, that's pretty strong evidence that the flame speed is independent of the combustion time. And we took that to be evidence that these particles are burning in the discrete regime of particle combustion. And these space experiments were not the only ones to give us evidence of this new type of combustion physics, right? The discrete flame regime, the first evidence for it is basically, or the first prediction of that theory is that the flame speed will be independent of that combustion time. In previous experiments on the Falcon 20 aircraft, microgravity experiments, you can see here, performed by Francois Tang, showed that also for a variety of particle sizes, there was not any observable difference between flames burning in 20 and 40% oxygen and xenon. In some experiments we did on aluminum combustion with my student Philippe Julien and others, these are aluminum flames propagating in transparent balloons. Variations in oxygen concentration caused a large difference in flame speed for rich flames, but down here in the lean region, all of the flame speeds collapsed. Andrew Higgins also had a student, Alex Wright, who did some experiments of aluminum and magnesium flames propagating in tubes on the ground. And there, again, did not see any variation in the flame speed with oxygen concentration. And of course, Michelle, my student who's studying the iron flames, also showed the same thing. So there's a good amount of evidence that indeed metal particles burning under these types of situations, whether it's small particles or large particles, whether it's iron or aluminum or magnesium as a fuel, there's strong evidence that these metal flames often burn in the discrete combustion regime, and that these physics are going to be important for any type of practical application. That experiment, now we want to go further and start to understand what is the impact of these physics at the limits of the flame propagation. So as we go towards the lean concentration limit, how does these new type of combustion physics impact the flame propagation? And so you can see here a flame propagating at higher iron concentrations, and you see that it develops this sort of parabolic shape that we're used to seeing in flames propagating inside of tubes. But whereas when we go to the lower concentrations, that structure, that uniform structure and that smooth structure of the heat release field really breaks down, and you see particles that seem to be igniting and burning almost randomly and at different locations that are outside of the envelope that we might say is existing here for the flames. So that's the focus of a second follow-up flight that we performed in 2020 on the Texas 56 rocket just before the pandemic. And here's one high-speed video. That experiment involved a high-speed camera zoomed into a part of the flow. And in this one specific video, we see that the flame was propagating inside of the whole tube, and then it hit a spot where there was a lack of particles, the concentration was lower, and it climbed through the top. And the way that this high-speed camera was triggered was when the light intensity in this initial part of the field of view reached a certain value. And so we got lucky. We actually had 2 videos recorded for the same flame propagation process. So the flame quenches in the lower part, propagates across through here. Then that was the end of our high-speed video recording. But then we caught a second high-speed video where that flame actually propagated down and propagated backwards to fill the rest of the tube and then carried along on its way. So in this case, that flame that was propagating through the whole tube found some path where it was able to survive without quenching, although it quenched through bulk of the flow, and then backfilled through the heat release once the temperature field was high enough. It was able to then propagate there. So that's evidence of some type of new type of combustion physics, right? It's related maybe to stratified flames and maybe related to some type of percolation-like phenomenon and or related to some other type of new physics that we need to understand. And so very interesting. And the focus of future efforts will be to really dig into this problem of what happens with these flames as we approach the lean propagation limit. But okay, so that's on the science, but now we want to do something practical, right? We said we wanted to develop these things in order to decarbonize our economy. And so we need to actually build some hardware to do that in a practical way. So in parallel, my team has developed a project to burn iron fuel, disperse it in air, burn it inside of a flame, capture the combustion products with a cyclone, take the oxidized fuel, you can see the difference in color between the unburned and burned fuel, recycled it with our partners and with hydrogen, and then used that fuel and burned it again and demonstrated that, in fact, we can indeed close this cycle and do it in a green way. And here's a video of a pure iron flame burning in air. There's no hydrocarbon fuels used in this except to just get the first ignition and to light up the flame. And then after that, the iron particles can burn in air in a stable flame structure with no other fuel inputs. And so that stabilization of that flame, that is very interesting, and that enables us to now think about taking this technology towards the market, and my students are now working to do that. We're not alone. Philippe de Hooy's group and Technical University of Eindhoven has been working on this. They're working with us on the PerWaves project and got bit by the metal fuel bug some years ago. Developed several different initiatives in a very large scale demonstration project. They were the first ones to show this. They burned iron fuel at a brewery to generate steam for the brewery in carbon-free heat. And that setup was at about 100 kilowatts of power, developed by Team Solid and at the University of Eindhoven, which was some student group started that. And then they've demonstrated and shown that this can be done in a practical way, and they're now spinning out a company, Renewable Iron Fuel Technology, to do this. And there's several other projects at Lund University in China. There's some projects, and Christian Haas and Andreas Dreisler have a large project out of the Technical University of Darmstadt called Clean Circles, where again, the same idea of clean reduction of iron oxides into iron particles and burning those iron fuels for carbon-free energy where and when you need it. And so there's a large amount of activity now going on in this area of metal fuels. And so I guess the idea of using metals as a fuel has ignited and is now burning independently of our group at McGill. There's not just interesting in metal fuels for Earth applications. In fact, actually, the long history of the idea of using metals as a fuel goes back to the ideas of in situ resource utilization for space exploration. Basically, on the moon or Mars, there's no life, there's no carbon, and there's no carbon-based fuels. And so you have to take use of what you have there in order to reduce costs of space exploration. So what you have is rocks, and rocks are metal oxides. And so you can use those metal oxides and reduce them using what's called molten regolith electrolysis or other techniques. You can power that, solar energy, nuclear energy, whatever energy source you have, and make metals out of those regolith, and then use those metals in order to generate propulsion systems that can burn either oxygen that came from the splitting of the rocks, or with the atmospheric CO2, because things like magnesium specifically burn well in CO2. And so you can now use those metals as fuels for sustainable space exploration, as well as for sustainable power here on Earth. So to close, I just want to bring a few ideas together. The first is that the concept of using metals as a fuel is really about building a fuel that you can burn, recycle over and over and over again. So where and when you have clean electricity, you reduce the oxides into the metal, you transport that metal fuel to where and when you need it, you oxidize it in a burner or in a metal water reactor to produce that power on demand, you collect the oxides, you bring them back, and you close the loop. If we want to understand the differences in the combustion physics, well, we have to understand that the fact that these particles ignite and burn heterogeneously means that it's a new type of combustion physics, different from hydrocarbon combustion and really different from coal or other types of solid combustion that we're used to. And that leads to new combustion physics called the discrete flame regime, where the particle combustion time or the reaction rate no longer is a controlling parameter. And that's difficult for us to understand as combustion scientists because it goes against what we're used to thinking about. But rather than closing on a series of conclusions of what we've learned, I really wanted to close this with a bunch of questions, because I think for the young people that are going to be watching this webinar, this is really an invitation to join in on this effort. And I think, as Christian Haas said during the preliminary discussion we had when we logged in, this is going to keep us busy for a long time, all the way to retirement and hopefully beyond just Christian's and my retirement for the young people. And that's because there's so many things that we don't understand. How does iron fuel burn? How does it burn in different types of oxidizer concentrations? There is evidence that you can form nanometric oxide particles. That's bad. That makes it difficult to capture and close that loop. So how can we suppress that? And there's work and efforts going on in that area. And there's a lot of research activity that we're seeing now. What's the effect of these different types of metal fuels? What is their flame speed? How does that depend on particle size and other types of variables like oxidizer concentration, et cetera? When we go into a turbulent flow, what is the effect of the flame stretch, the particle slip on those heterogeneous flames? I mean, now we've got heterogeneous turbulence, a hard problem, and heterogeneous combustion, very difficult problems to solve. What's the effect of preheat on these metal flame speeds? We had one student in our team look at that initially for aluminum, but as far as I know, there's been no other work on the effect of preheating for these different metal flames. We actually see a lot of evidence of flame instabilities. How do those instabilities form? How do they impact burning rates in both laminar and turbulent flows? What are the flame propagation limits? How do these discrete effects impact practical combustion systems? And there's lots of other questions that we have. And so if you're interested in those, Sam, Jan, and I published a paper in Progress on Energy Combustion Science recently that talks about what we know and also talks really about what we don't know. And I invite you to look at that paper to get some inspiration for other research questions that we can bring in. So with that, I'd just like to thank all of our sponsors that have supported this work over the years, especially the European Space Agency and Canadian Space Agency that really have supported this work for 20, 30 years at McGill, well before my time. And, you know, none of this work could be done without a great team. Here's a picture, the last one we took before COVID, so we haven't had time to take a new picture recently, but this is my research group. I also wanted to thank the collaborators that we have, Philippe Dehoy, Marcus Alden, Martin Schiemann, Fabian Halter, Evgeny Shafirovich, and others involved in this ProWaves project, and especially Andrew Higgins and David Frost for getting me interested in studying metal combustion. And I also wanted to especially thank Sam Garoshin because he's the one many years ago asked me, what happens when we put metal particles into a hydrocarbon flame? And we came up with a hypothesis and we wrote a grant proposal. We did the experiments. Our hypothesis was completely wrong. I guess that's science, and we learned a lot from that, and that gave me the bug to keep understanding and trying to study metal combustion physics, and it's been a very rewarding and interesting journey. So I really owe a lot to Sam for his guidance in this research field. So with that, I'm going to put up some cool videos that will play here as we go. Didn't have time to talk about all the types of experiments that we've done in this area, but there's a wealth of experiments that we've done to try to understand these combustion physics. And I'd be very happy to take questions and have a discussion with you about this topic. Thank you.
Thank you, Jeff, for this very interesting and very informative talk, and especially this encouraging invitation for the young researchers to keep working in this field to tackle all these unknowns. Thank you. I already see a number of questions in the chat. Maybe let's go through this. And in the meantime, please, I also invite the audience to type your questions, or the panelists also unmute yourself or raise your hand to ask a question. So let's go through these questions or comments in the chat. The first one is from Professor Jay Gore. Well, if he's in the panel, so if he wants, he can unmute himself to directly ask.
During the talk, this was very clear, and also in the conclusions that the primary source would need to be solar, wind, geothermal, or hydro. I did want to ask a question for our distinguished speaker as to what his thoughts were on nuclear.
Well, nuclear is always a tricky one. You know, I think if we can get nuclear fusion, then we're going to be having lots of good, hopefully cheap electricity that will make metal fuels another important option inside of all of this. Standard nuclear, small modular reactors, I'm less convinced. I just think that the cost traditionally has been extremely high for nuclear power, and I'm not convinced that the efforts that are going into this today are going to solve that. And I just, you know, and I worry about the waste and the sustainability of that processes. So I'm not against it. I think we need to decarbonize primary power generation. If nuclear is a part of that solution, then great, let's do it. And then that doesn't, I don't think, obviate the need for metal fuels. I think we'll still need other solutions in this to transport and store that energy, because I don't believe we want to put nuclear reactors on every ship, for instance. I think that we need to have other carriers of energy for many other applications.
Thank you, I agree. And while I had the mic, one quick question about, what do you think about utilizing metals to reduce CO2 in terms of perhaps not giving up on the entire hydrocarbon economy, but taking responsibility for the CO2 and reducing it, utilizing perhaps metals to oxidize the metal, reduce the CO2, and certainly primary energy sources would need to be renewable in that process as well. Or I think in the periodic table, you struck carbon and hydrogen as possible elements for the overall energy cycle. Is that essential, or could those elements remain in the overall energy picture for the foreseeable future?
Well, thanks for the question, Jay. I think, in terms of aerospace propulsion, I don't see any alternative to hydrocarbon fuels for aviation. And so I think we have to keep using hydrocarbon fuels, whether those are bio-based or e-fuels that are produced from carbon capture. I think that is going to be necessary into the long term. I'm not a believer that we're going to simply electrify aircraft with batteries and be able to have the same type of transport system that we have today. So I think hydrocarbon fuels will continue to fill very important roles as we go forward. And I think we need to find ways to displace them from the other applications. The other question that you had was really more about, can we use the metal fuels to reduce the carbon dioxide emissions? And we did some work on that with Martin Scheeman, looking at lithium combustion in CO2 or in the products of, say, a coal-fired power plant, and then using that to upgrade and making syngas. And so there is possibilities to do that. The economics are difficult on that. And so you have to find the right type of system to be able to enable those metals to upgrade, let's say, the hydrocarbon combustion products. But the other side that's very interesting is to think about it related to chemical looping combustion. And there you could actually use hydrocarbon fuels to reduce the metals where you have hydrocarbons and then sequester the products, the carbon dioxide. And if you do that, then you can still use the energy in the hydrocarbon fuels without the carbon dioxide emissions, and then move that energy away in the form of these metal fuels. So I think there's lots of interesting ways to think about the cycle, and that process can be done in different ways to go through the transition process, right? From where we are today to where we might be in 100 years. And I think the flexibility of the metal fuels is actually quite an interesting opportunity there.
Thank you, Jeff. And I think your presentation is exciting and encouraging for not just the young audience, but also the not so young audience. Thank you.
Well, I saw the poster, and I know I saw the poster for the talk and realized that I'm not so young either anymore. So, but thanks, Jay.
Yeah. Thank you, Professor Gore, for the question. And the next one is from Hailin Li. His comment is an excellent topic. A quick question: have you estimated the energy loss during this process? We can assume the metal is produced by recycling the combustion product.
Yeah, I mean, it really depends on the metal and the process by which you do the production. So that can vary from around 50% efficiency of renewable energy into chemical energy for the least efficient processes. If we go to electrolysis, especially at low temperatures, it can reach efficiencies like hydrogen production, 70, 80% efficiency of storage of clean energy into the metal fuels. On the use side, well, we don't really have any engines or power systems developed at any reasonable efficiency to say what is the possibilities. But thermodynamics tell us that's going to be between 30, 40, 50% at the high end. Maybe at very large scales, we can sort of approach 60% thermal efficiencies. So the overall cycle efficiency could be like 25, 30, 40%, somewhere in that range, which is clearly lower than batteries. It's about comparable to the use as hydrogen as a green fuel. And I think that's sort of the thermodynamic cost that we have to pay in order to have that energy where and when we need it. And you know, I think it's important to realize that, you know, if we waste some renewable energy, it's not the worst thing in the world, right? I mean, wasting electrons and photons is much better than wasting carbon. And I think we should keep that in mind when we're thinking about, you know, what's the importance of these efficiencies.
Yeah, thank you for the question and the answer. The next one is from Tiegang Fang. I think this is also an interesting question. Thank you for the interesting talk. Can you comment on the applications of metal particles or their water slurries in transportation engines like gas turbines and internal combustion engines? Thanks.
Yeah, so internal combustion engines and metal particles or metal oxide products really don't mix, right? You don't want to put these things through the moving parts. So that was why we proposed these two different concepts that involve keeping the metal reactions separate from the moving parts of the power generation equipment. Maybe someone will come up with an idea. There was work that was done to burn nanometric iron particles in reciprocating engines by a group in Greece, and they did some of this. But for me, I think you really want to separate those two. But if you use the metal water reactor and collect the oxides and you have hydrogen and steam, then for sure you can burn it in a gas turbine engine and in reciprocating engines, or use it in a fuel cell or in a steam engine. And so there's definitely possibilities to use those products, just like we've been developing for the hydrogen economy. Just think about it as a way of generating that hydrogen right before you use it, and then you don't need to store a large amount of hydrogen. So that improves safety and various other system type of improvements.
Okay. Thank you for the answer and also the question. The next one is from Professor Stephen Sun, and it's also regarding the economies. Please unmute yourself. You can ask.
Yeah, just real quick, Jeff. I mean, I have two questions really is, you know, what the most significant technical challenges are remaining. And I think you kind of answered that on the previous slide, and I typed this in before you put that slide up. And I would just second, I think the turbulence and looking at the effective turbulence and the range of flammability and stuff would be, you know, very important. And then the second part was on the economics. I've seen some estimates if you take the cost of, say, aluminum and compare that to the cost of hydrocarbon fuels, it's still significantly higher. So if you can talk
especially
about
today, the cost of aluminum is very, very high. And so really you have to be able to close that loop and come up with the economics, not so much of aluminum as a commodity, but as aluminum recharging. What's the cost of the recharging? Because the material's not lost. And so that's something that we've been looking at. And with aluminum, it should be possible to do the recycling at a cost that's competitive, but it's not been demonstrated so far. So some preliminary work on that area has been done that suggests that, yeah, you can do it for costs that are competitive with diesel fuel if you can close that loop and not lose that material. For iron, you can buy iron powder right now from Alibaba, and it's cheaper per unit of energy than diesel fuel. It's not green, but it actually looks like the economics for iron as a fuel are very competitive and can probably be produced at competitive prices today. So there's been a few pieces of work on that and some more work that's ongoing that I know of that suggests that, yeah, you can use iron as a fuel that's economically competitive in the very short term.
All right, thanks, Jeff. That was great.
Thanks.
Yeah, thank you. And due to the limited time, maybe I will skip the next question also regarding the economy. Let's move on to a more technical question from Wang. He said, "Hi, Professor Bergthorson. Thanks for showing the fascinating metal flame. I have a question about the flame temperature. It seems for larger particles, the flame temperature near macroscopic flame front could be higher than the calculated adiabatic flame temperature. Could you please comment on it?"
Great. Yeah. So that's a great question. So basically, if you're burning these metal fuels under fuel lean conditions, then the adiabatic flame temperature would be lower than the stoichiometric flame temperature. And if the particles ignite, they burn locally as a diffusion flame. And as we know in hydrocarbon combustion, when we burn a diffusion flame, it finds the stoichiometric surface and it burns at the maximum possible temperature at the stoichiometric adiabatic flame temperature. So that's why in those animations it showed that if you're burning an equivalence ratio of 0.5, well, then your temperature of your particles or your microflames can be twice as high, or the difference can be twice as high as the adiabatic temperature of the mixture. So there's a difference between the adiabatic temperature of your overall mixture and the adiabatic and the stoichiometric temperature if you're fuel lean. If you're burning fuel rich, now the temperature of your adiabatic mixture and your stoichiometric temperature are very close. And that's because when you go fuel rich, you really don't displace oxygen when you have more and more metal particles because they're so dense and as solid. So in fuel rich side, the temperature of the flame doesn't really drop off as it does for hydrocarbon fuels, because in hydrocarbon fuels, the gaseous fuel displaces oxygen. And as you go more and more fuel rich, you have lower flame temperatures. But for metal fuels, that doesn't really happen. And so on the fuel rich side, you probably are burning the particles very close to the temperature of the gas, even if they are igniting and burning in a diffusion regime locally. And of course, they're also consuming oxygen during that process. And if you're fuel rich, by the end of the combustion time of those particles, as they're burning out, there's no more oxygen available. And so that also limits that temperature separation. So you really would only see that temperature difference under the fuel lean side.
Great, thank you for the question. I'm wondering, Wenting, do we have enough time for 2 more questions? I think there are 2 more technical questions left. Okay, great. And one more, this is from Ahmed Sayed Kassan. He said, thank you for the impressive presentation. Do you have an example of aluminum combustion in industrial or semi-industrial scale? And if we have to choose between aluminum and iron, which one is the better?
The only examples of aluminum combustion at large scale that I know of have been in industrial explosions. So I don't know of any practical and green use of aluminum at larger scale. So it's really only been in accidental scenarios. And I think I see that maybe that's the next question. So we'll talk about that a little bit later. In terms of which is better, well, better depends on your application. So I think that there's no silver bullets in this energy transition, right? We're not saying that metal fuels are better than solar panels. You need solar panels and you need metal fuels, and you need hydrogen, and you need hydrocarbon fuels that are carbon neutral, and you need metal fuels. I think we need all of these solutions together. And so I see that there's very different mission profiles for the 2 fuels. I think aluminum makes a lot of sense for when energy density is extremely important because it has more energy per volume and mass. And so maybe shipping, maybe propulsion applications as it's already used, and maybe for remote power generation where you need to bring a large amount of fuel, say once per year in the northern Arctic parts of Canada. There's applications I think where aluminum makes the most sense. For other applications where you maybe need to transport it over shorter distances, maybe store it over longer times, maybe then iron is the more effective solution. So I think depending on the application, the right fuel will be found, right? And if you want to store energy from day to night, batteries will make sense. And if you want to store it from today till 2 days from now, maybe hydrogen's the right solution. So I think each of these will have a range of applications. And by having all of these possibilities, we'll be able to make this transition. So I think it's an all of the above.
Yeah, thank you. And this naturally leads to the last question regarding the safety of metal powders as a fuel, whether spontaneous combustion in air is possible or a problem.
So absolutely. So there's been large scale industrial accidents associated with metal powders. For sure, there's a safety risk, especially the finer the particles that you use, and especially aluminum compared to iron. Iron's actually quite hard to burn. We took a long time to be able to stabilize that laminar flame of even micron-sized iron particles in air. So to me, iron is much safer than aluminum. And what we really want to do is to try to find ways to make it safer. And so that was the approach that we took, was rather than going to this propellant type mode of nanoparticles of aluminum burning, say with water, we actually looked for a way to make the reactor be able to digest bulk aluminum or very large scale powders that are much safer. So that was one of the key drivers behind our look to try to find conditions where we could use aluminum that's basically safe. I mean, aluminum foil that you have in your cupboard could be used as a fuel in that case, and we're not worried about that, right? And then in the case of iron, also there, I think, the key advantage is that if you can develop the type of combustion systems at large scale that can burn, tens to hundreds of micron sized iron particles, those are extremely difficult to get into an explosive range, and the safety should be very, very high.
Right. Okay, thank you, Jeff, for answering all these questions. I don't see any further questions. Yeah, there is a lot of appreciations and gratitude. Yeah, and I would like to thank you again on behalf of the whole audience. And I will hand over to Wenting.
Thank you, Xiaocheng. We've been working together on this for a long time, so I appreciate all of your inputs into this.
Yeah,
thank you very much, Jeff. This is really excellent presentation. I enjoyed it a lot. So let's turn on our camera and say thank you once again and to our presenter. So this concludes the last webinar for this semester. So we will take a summer break and hopefully we will resume in the fall semester. So stay tuned. Thank you.
Thank you, Wenting, and thank you to all the organizers for this. I know that the students really appreciate this series, so thank you for putting all this together.